Can everybody, ooh, sorry, can everybody hear me? Yes, it's not weird or anything at the back. Okay. Perfect. Welcome everyone to our last TSI public lecture of the year. Thank you so much for coming, and it's great to see everybody on this rainy day. My name is Hannah Fronenberg. I'm a PhD student here at the TSI in the McGill Physics Department. I'm also the TSI Outreach Coordinator and your moderator for tonight. Just a few quick things before we get started. I just quickly want to flash on the screen some important information. So of course, during this whole discussion, whether with the speaker or with each other, we hope to make sure that everyone feels nice and comfortable so that we can share all of our awesome astro information. So if you have any concerns throughout the night or feel uncomfortable, you can come to me or to any of our volunteers who have a little pin that say, ask me, I'm an astronomer. So if you have any questions, you can come to us. I'd also just like to flash our code of conduct. I'll just leave this here for a moment for everybody to read. And last, before we get started, don't forget to fill out our form where you can win a MSI hat and mug, which is very valuable now because our institute has changed names as of last week. So these are never going to be made again. So these are now antique, collectible, MSI, McGill Space Institute hat and mug. So please, I'll leave this here for one moment, so get out your phones if you haven't filled this out already. So with that, I am so happy to introduce our speaker, Natalie Ouellette. Natalie is the outreach scientist for JWST in Canada and the deputy director of the Institute for Research on Exoplanets, which recently also was renamed. So it should be now the Trottier Institute for Research on Exoplanets. She's also the deputy director of Mont Mégantic Observatory at the University of Montreal. So tonight she'll be teaching us about the first discoveries from JWST. In just one short year from launch, the data taken from JWST has already changed the way that we think about our universe. And there's no doubt that as new data comes in, our intellectual horizons will continue to expand in unimaginable ways. After the talk, we'll have a Q&A session, and you'll have the chance to ask the speaker all of your most pressing JWST questions. And if you're joining us on YouTube, just type your question in the chat and we will relay it to the speaker. So without further delay, Natalie, we're so excited. Oh, yeah. Yes, I will send, yeah, I can send you the
Give us like 90 seconds. You're going to send it to me by email?
Yep.
Man, that's an active mic. Yeah, I feel like I'm going to blow this mic out. No? This is a reasonable volume? Okay, perfect. All right. I just need to sign on to the Zoom link so that the lovely people online can also see the slides that I'm talking about. And the host just needs to let me in. Can you see that online?
Yep.
Turn my sound off. Now I got to take care of you people so that you can see it. Okay, move that to the side. All right, is everyone happy?
Yeah.
Oh, I need to reshare. Okay. Okay, so the people online are not happy.
Oh wait, now it's good.
Oh no! Oh, but now I stopped sharing. Oh no! It was working and then we ruined it. Is that good?
Yeah.
Okay. I can hear myself from my computer, even though my sound is off. Good. No, I can still hear myself. That's really trippy. I don't know if I'll be able to like ignore that.
Yeah, but the owl mic has to be on for people online.
Okay, I'll try to ignore myself, which is a strange concept. All right, I'm so glad to be here tonight to talk about the latest results from the James Webb Space Telescope, the JWST, or the Webb Telescope. So thanks for coming out. I know it was a not so nice day outside and it's still very windy, so I'm gonna assume you're all blown into the building and this is why you're here right now. But I'm glad we're in a big room because I know it's tough times right now. A lot of viruses are going around, but you're still able to come and enjoy this talk. So I hope I make it worth your while. I always like to start my talks by saying that astronomy is a science that is very democratic, in my opinion. We've been doing it for a very long time, for millennia, because it doesn't really take any tools to do it. So we've been able to go outside and look at the stars for the longest time and ask ourselves really deep questions like, are we alone in the universe? Or where are we in the universe? What was at the very start of the universe or even before those beginnings? And so we've been able to build on that knowledge for a very long time just by looking at the sky. But of course, humans are defined a lot by the tools that we create. It allows us to build on that knowledge. And the tools that are the most associated with our profession as astronomers is certainly telescopes. So we put other instruments on the telescope and everything, but telescopes is something that we've had now for hundreds of years that have allowed us to look at objects that are fainter, farther away in more detail. But there's another part of the equation why telescopes are very important, and it's because the universe is shining in lots of different kinds of light. So this is what we call the electromagnetic spectrum. So we are used to one specific part of that spectrum called visible light. So visible light is the rainbow that we can see if we break apart sunlight from a prism, and you can see it right at the center here. But that's a very small part of all the different types of light that the universe can create. So you have in this area here, radio waves. So radio waves we often associate to sound because that's what we use for telecommunications, but radio waves are just another kind of light. And they are the longest wavelength light, the lowest energy. If you go a little bit higher energy, you can get to infrared here. And these are all invisible to the human eye. And if you go to even shorter wavelengths, shorter than the visible, you have very, very short energetic wavelengths where you have ultraviolet, X-rays, gamma rays. And so you may be familiar with a lot of these. We hear about them on a daily basis, or we use them. X-rays are very associated to medicine. We know that we have to protect ourselves from ultraviolet light. But we really tend to operate in the visible wavelength in general. But that doesn't mean that there aren't super interesting phenomena in the universe that are shining at these different kinds of light. And because we cannot see it with our eye, we needed to build special tools, special telescopes and cameras and detectors to look at those types of light. But there is another challenge here, and that is the fact that we live on the Earth in a protective atmosphere. Now, we love the atmosphere. It allows us to stay alive, because we're breathing the atmosphere, of course, but it also protects us from a lot of these harmful kinds of light. So especially the very short wavelengths that I mentioned, ultraviolet, X-rays, gamma rays, those are things that can change our DNA and cause cancer over time. So we want to be protected from that, and luckily we are. So this is a graph that shows you how transparent the atmosphere is for different kinds of light. So the more brown you see, the more the atmosphere is blocking that kind of light. So there are two main windows in the atmosphere that we have. We have this one right here, which is the visible wavelength. Luckily, that's what we use, but it's not a coincidence really. It's because the sun shines most brightly in that type of light. So through evolution, this is the kind of light that we've adapted to use for our eyesight. And we have another window right here, which is radio. And it's no wonder that we have adapted radio for telecommunications, because it can travel through the atmosphere without any issue. So that's really good as well. But everything else on this graph is blocked out, at least partially, by our atmosphere. So in order to get any information in the ultraviolet X-rays, in many parts of the infrared, we need to go above the atmosphere. So I can ask you right now, at least for this kind of telescope, what's the best place to put a telescope, according to you? Space. In space, exactly. So space is a really fantastic place to put a telescope. And of course, there are a lot of challenges in putting something up in space. It's more expensive. It takes a lot more time to construct typically. And once you send it up into space, it's very hard to start fixing it or repairing it or adding things on. It's not impossible, as we've with this particular space telescope in the image, the Hubble Space Telescope, but it is quite costly, quite challenging. So it is actually very important to have telescopes in both places, on the ground and in space. They're complementary, essentially. But we will be focusing on space telescopes here. And I can't talk about a space telescope without talking about the one that I grew up with, the Hubble Space Telescope that you can see here. So Hubble was launched in 1990. And some of you may know or might remember firsthand that it had some rough beginnings because there were a lot of issues with its mirrors. And so the very first images that came out didn't necessarily blow us away the way that the images from the Webb telescope are really blowing us away right now. They were quite blurry and fuzzy. So it wasn't until 1993 where a team of astronauts, including some astrophysicists, went up into low Earth orbit, where luckily Hubble was located around the Earth, to fix the mirror of the Hubble Space Telescope using the first Canadarm. So a lot of people don't know that the first Canadarm was actually essential in fixing the telescope. Since then, Hubble has done incredible things, not only for scientific research in astronomy, but also for the public's perception of astronomy. So I grew up with these pictures. They were really fantastic. We have the Pillars of Creation here, the Orion Nebula. We have two colliding galaxies called the antennae. These are my favorite objects in the entire universe, really fantastic. And a lot of astronomers, especially of my generation, became astronomers because they fell in love with these images. Now, Hubble is sort of like a big, giant human eyeball. It has a mirror that's 2.5 meters wide. I find that often with pictures and telescopes like this, you don't have a sense of scale. Hubble is about as big as a school bus, so it's still quite large. But we wanted to go bigger, and we wanted to look at a different kind of light. So Hubble looks at visible light. That's why it's like a big human eyeball. We wanted to look at some of the type of light that the atmosphere is blocking out. So basically, when Hubble was just getting its stride and really doing a lot of research in the mid-90s, we already started thinking about the successor to Hubble. I say successor, not replacement, because it's not our intention to retire Hubble prematurely. It's still doing incredible science. And again, we want a lot of our missions to be complementary. So Hubble looks at visible light, and the successor that we wanted to build, the JWST, looks at infrared light. So if you're looking at the same object in both the visible and the infrared, you are getting twice as much information. So really fantastic. But for the JWST, we really wanted to knock it out of the park and make a really huge telescope. So this is the largest telescope we've ever sent to space. And you can see it has a very, very unique design. And I'll explain a little bit why it looks like that. So this is a mission that's led by NASA, which was the same thing for Hubble, with an important contribution from the European Space Agency, also a contributor for Hubble. But importantly for us, and exciting for us, the Canadian Space Agency is a member of this collaboration, and an important member too. So it's really fantastic. This is the largest space astronomy mission Canada has ever been involved in, and I hope it's just a blueprint for future missions. So I am the outreach scientist for the mission in Canada. Now, what does that mean? Outreach scientist is luckily a role that is becoming more and more common with time. People are realizing that it's important for the public to understand the science that researchers are doing. So I'm part of the science team. I have a background in astrophysics. I study galaxies, but I act as a bridge between the science team and the general public, because it's public funds that made sure that Canada could be involved in this fantastic mission. So this is a picture of me visiting the telescope in 2019. While it was still being tested, before it was launched into space. Obviously, I'm not in space right here. It was great, and being able to see the telescope in person really gave you that sense of scale. So its mirror is 7.5 meters wide. The sun shield, the sort of silver foil you see, that's as big as a tennis court. The whole thing is about 2 stories high. So it really is like the size of a small house. That's floating around in space now, taking these images. So it's really fantastic. So I like this picture a lot. But the picture that I like showing that shows my dedication to the mission is this picture. So this costume, not this year. I took a break this year, last year. And I decided I wanted to be the JWST. So I made this out of cardboard and foil and tubes and all kinds of stuff. And it's to scale and everything. And I gave out candy. And so I think it's important that different people do research and do outreach with their personalities in mind, because we can reach out to different audiences and see these really complex problems from different points of view. So yeah, it's more than just a mission to me. Like, this is my life. The telescope is really important, but it was really fun. And the cardboard costume is now in my office at the University of Montreal. So after decades of preparation, we were finally able to launch the telescope aboard an Ariane 5 rocket almost a year ago now. It's hard to believe that it's been almost a year. So there were a lot of delays during this mission, but with good reason. The Hubble Space Telescope, luckily, is in what we call low Earth orbit, about 500 kilometers above our heads, which made it repairable when we wanted to fix its mirrors. But because Webb is an infrared telescope, the Earth actually shines quite brightly in the infrared. So we needed to launch it much farther away, about 1.5 million kilometers away, which means that if something went wrong, we could not fix it. So we needed to test it very extensively. And if there was even a glimmer or a hint of an issue, we needed to stop everything and make sure that everything was okay. So with all those delays, the launch date ended up being December 25th, for Christmas morning at about 7 a.m., 2021, so nearly a year ago now. And you might remember 2021, around the holidays, it was a super cheerful time. And we were right in sort of like the crest of the Omicron COVID wave. I know I don't want to talk about COVID, but like, you know, it's a reality that we had to deal with. And so a lot of the members of the team actually were planning on being in Peru, in South America, where the telescope was launched. I was supposed to be in Baltimore, the control center, where they would start controlling the telescope, but we had to cancel our trip. So we instead got to watch it from our homes for the most part. We were still connected to the comms link and everything to hear what was going on. But how many of you got to watch it? Well, got to watch, made yourselves watch it and forced your families perhaps to watch it on Christmas morning last year? Yeah, that's great. So some dedicated folks here. That's fantastic. So There's a quick clip here, so we'll watch some of the important parts again right now.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight. Good pitch program reported.
Trajectoire est nominale.
So you might notice that the countdown and the narration was in French. That's not because we're in Quebec and we're forced to like show you or anything like. No, the launch actually happened in Peru, French Guiana, and the launch site and the Ariane 5 rocket was one of the contributions of Arianespace and the European Space Agency. So that's why the countdown was in French. So it was a fantastic launch. A lot of us were very nervous because, of course, this was a lot of people's life work on a giant rocket and blasting up into space. But it was perfect, essentially. And they actually saved a lot of fuel during the launch and the subsequent course correction, so much so that they were able to extend the lifetime of the mission from about 10 to 20 years to double the lifetime mission because the fuel was really the limiting factor. So as I mentioned, I was really looking forward to celebrating this moment with all my colleagues, but I still got to watch this with my family, my partner at home. And so my partner had the idea to commemorate this event, and he filmed me watching the launch. I won't show you that video. One screen capture to show you sort of like the feeling we were having in that moment. You can see I was very nervous. For those of you who watched the launch, I can tell you exactly what moment was happening here. It's when the outer fairing, the outer shell pops off the telescope, and the telescope is open to the elements for the first time. And obviously they do this at a reasonable time where like it's not going to get damaged, but you know, you still feel an emotional reaction when you see your baby uncovered in space for the first time. And so I was nervous and I was emotional and I was happy and all kinds of emotions inside me, but in the end, it was a really fantastic launch. Of course, that was only the start of the adventure. And the real thing that we were worried about, more so than the launch, was the subsequent deployment. So because this telescope is so big, again, about the size of a house, we needed to fold it up on itself so that it could fit inside the rocket fairing that launched it into space. That means that if you fold it up, well, if you want it to work, you need to unfold it essentially or deploy it. So this is what we call, sort of colloquially in the team, the 14 days of terror, sort of a spin-off of what we call the 7 minutes of terror. That's how long it takes to land on Mars. And usually you can't control anything that's going on. It has to be done independently. So these 14 days of terror were where the telescope needed to deploy over 300 single point failure mechanisms. That means over 300 things that could go wrong and sink the mission before it even started. This is why we tested it extensively. We've never done something so complex in space, remotely, with so many mechanisms that could fail. But it was worked into the configuration of the telescope from the get-go, because we knew we needed a big telescope, so we knew we needed it to be foldable and unfoldable. So there are many important components here that we can see, and the one that made us the most nervous for the unfolding is the one that is currently deploying. It is what we call the sun shield. So I mentioned Webb is an infrared telescope, which is why we need to launch it so far away, 1.5 million kilometers from the Earth, but that's not sufficient. If the telescope is in the sunlight, it will eventually heat up itself and start radiating in the infrared, causing its own light pollution. And imagine spending $11 billion, you send it up there, and then it's like radiating its own light pollution. You can't see anything other than its own glow. That would be disappointing. So the sun shield was a very, very mission critical element. It's 5 layers of a very reflective material called Kapton. and their protection equivalent is of a sunscreen lotion with an SPF, a factor of 1 million. So it's a very, very protective shield or sunscreen lotion that is protecting the mirror and the instruments from the sun. And for the most part, that is sufficient to keep the telescope very cold enough so it doesn't radiate its own infrared lights. It keeps it at about minus 230 degrees Celsius, so colder than our winters even. But there is one instrument on the telescope that actually needs to be cooled further, so that there are additional refrigerants in it that bring it down to about minus 265 degrees Celsius. That's about 7 degrees above absolute zero. You'll also notice the mirror, very unique looking mirror. It's actually made up of 18 separate segments, all coated in gold, which is very reflective in the infrared. And each of those segments can be moved independently. So if ever there was an issue with the mirror, like we had for Hubble, we are able to move and reshape the mirror by moving the individual segments. So that was very handy as well. So this is Canada's contribution to the mission. It is a double instrument. All the instruments are located on the back of the mirror in what we call the instrument module. And there are 4 instruments total. And the Canadian one is right at the heart, right at the center. So we actually had to deliver our instrument first in 2012. So the top part of the instrument is what we call a flying guidance sensor. It's not a scientific instrument, but it's mission critical. So its role is sort of like acting like an eye for the telescope. So we have a Canadarm on the International Space Station. We have a Canadi on the Webb telescope. So if you have a telescope at home, maybe you know that there's like a little viewfinder or finder scope up top, which allows you to sort of roughly find what you're looking at. And that there are mechanisms, if you have a computerized telescope, that can lock onto a target and compensate for the rotation of the Earth. So that if you want to, for example, take a long exposure of what you're looking at through the telescope, you're not going to have those like sort of weird lines caused by the movement of the Earth, which is perceived by the movement as the movement of the stars for us. So the same thing happens with professional telescopes too. The JWST is actually moving around in space, but it wants to take a fixed picture of a celestial object. So this guidance camera is actually feeding information to deformable mirrors on the telescope at a rate of 16 times per second to compensate for that motion. And so even though it's not a scientific instrument, it's mission critical. And every time you see a picture or a result coming from the telescope, it was enabled by this Canadian eye. So it's a really fantastic tool and very important to the mission. On the bottom part there, you have a scientific Canadian tool called the NIRISS, or the Near Infrared Imager and Slitless Spectrograph. It's a combination of a camera or a detector and a spectrograph, which I'll talk about in a moment. So this whole contribution was orchestrated by the Canadian Space Agency with many, many partners, hundreds of people throughout Canada who worked on this for decades. The main academic partner was the University of Montreal, where I work. We also had an important partner at the National Research Council, which is in Victoria, and the main industrial partner was Honeywell Canada, which was formerly ComDev at the start of the mission. So a little bit closer to home, this is the University of Montreal team, or Université de Montréal. And we have here in the center, Professor René Doyon, who is the principal investigator of the Canadian instrument on the JWST. So this is just a snapshot of some of the people that have worked on the telescope or are now working with data from the telescope. This was taken about a year ago. There are people that have come and left the mission, and more people will be added on in the future. But what I love to point out here is all the young faces, even younger than me, that you can see in this picture. And a lot of these are graduate students, master's and PhD students, who are working on JWST data, some of the first astronomers in the world who get to play with exoplanet data from the JWST. And they're doing their master's thesis and their PhD thesis on that. So they're in a very enviable position right here in Montreal. And we even have summer interns who are doing their bachelor's working on JWST data and simulations. So that's really exciting. So the University of Montreal is a really great place if you want to be a collaborator on a lot of these programs. So what has the telescope been doing since it was launched nearly a year ago? It has been doing lots and lots of things. So the first 6 months after the launch was the deployment, and then another 5 months of a phase we call commissioning. So commissioning is basically making sure the telescope and all of its instruments work. So you're turning everything on, you're doing lots of tests and calibration. But one of the key parts we have to do was aligning Webb's mirror. And I mentioned there are 18 separate segments that can be moved independently. And when it's first launched, each of the segments is doing its own thing. They're not working together. So instead of having one massive 6.5 meter wide telescope, you have a bunch of small 1.2 meter wide telescopes. So not that useful, not that impressive. So what we do is we take all those little segments and we move them independently. We adjust and align them so that they are acting as one. So we point the whole thing at one bright star. At the start, we see 18 bright points, and then we move all the segments until we only see one single point. At that point, we know that all the segments are acting as one single giant mirror. And so we lock that on, we make sure that it's working well and is aligned for all of the 4 different instruments on the telescope. So ideally, we would do this only once, but of course, that's not how it ends up working. So over time, there are small adjustments that need to be made. For example, if we get hit by a micrometeorite, which has already happened several times, we can change some of those segments, the alignment, so that we can compensate for some of that damage. And that damage has been very, very minor up until now, so there's no worries there. So this has been all about the technological wonder and the mission. But of course, Webb is a telescope, a scientific tool, and we're interested in the kind of science we can do. So we can break down that science in 4 main categories. The first of which is alien worlds, and that can include things in our solar system. So anything that is beyond the orbit of Webb, or essentially beyond the orbit of Mars, is accessible to Webb. Webb cannot look towards the sun because then would foul its instruments because it's no longer protected by the sun shield. So Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, a bunch of comets and asteroids, they're all accessible. But we're also interested in exoplanets, which are planets that are beyond our solar system, worlds that are orbiting other stars. We want to understand how many of them are there, how they form, what their diversity and range is, and also what their atmospheres contain and if they could be habitable. We're also interested in stars from the moment they were born all the way to their deaths. So the life cycle of stars, where we're looking at stellar nurseries where stars are being born, all the way to if they blow up into a supernova explosion and leave behind very, very exotic compact objects like neutron stars, pulsars, black holes. Black holes, always a crowd favorite. We want to do something similar with galaxies as well. So galaxies, this is my field of research. Galaxies evolve over time, over long time scales of many tens of billions of years, and they often interact with each other as well. They're oftentimes in groups where they will harass each other. That's the technical term. It's galaxy harassment, collide, merge, all kinds of interactions. And we want to really get a full picture of how galaxies evolved through the history of the universe. So that includes looking at galaxies that are very close to us in the local group, all the way to the very, very first galaxies that were born just a few 100 million years after the Big Bang in what we call the primordial universe, or the early universe. So already with Webb, we have been able to push back how far we can see in the past of our universe, because astronomy is kind of a little bit weird. The farther you look in distance, the farther you're looking back in time as well, because of the finite speed of light. So a really cool little magic trick. With Hubble, we were able to look at about until 500 million years after the Big Bang. Already with Webb, we've been able to push that to 200 to 300 million years after the Big Bang. Now that doesn't sound like a huge improvement, but the early universe was extremely active. Galaxies were colliding and merging and forming stars at very, very high rates in the early universe. And we are very interested in solving a lot of the problems we have when we're looking at sort of like the middle universe, where things look too big. We don't understand how galaxies got so big, so large. So we need to look at their beginnings to understand that. And we've actually been able to study some of those very first galaxies already. And we have some answers, but we have even more questions now due to some of those results. So talking about alien worlds, this is the team that I work with at the Trottier Institute for Research on Exoplanets. We're about 60 researchers, mostly based out of the University of Montreal, but also McGill, Université Laval, Bishop's University in Sherbrooke, and recently we also have some people at the Planetarium of Montreal. And so we're looking for exoplanets, exploring new worlds, and searching for life. So not searching for life like SETI in the radio waves, which you might be familiar with, but searching for what we call biosignatures. So an exoplanet is very simply a planet that exists outside of our solar system and orbits around a star other than our sun. But we're not able to study exoplanets with the same level of detail as the planets in our own solar system. So when we show you a picture like this, unfortunately, it's not a real image. It's what we call an artistic representation, but it's not pulled out of thin air either. We can actually tell a lot of information about exoplanets by the data that we do collect. We can tell often how large they are, what they're composed of, even if they might have ring systems. And we're starting to be able to tell if they even have what we call exomoons or moons around exoplanets. But we cannot see the exoplanets directly for the most part. We can only detect them with indirect methods, which means that we're looking at the effect that they have on the star that they orbit. And the most effective way to do this is what we call the transit method. So it's very similar to an eclipse. Essentially, we can stare at a star for a very long time, and we can notice that the star might dim periodically a little bit. And if it happens really periodically on a regular basis, it's a good indication that something is orbiting that star and blocking that star's light. And depending on how deep that dip is, we can actually tell how large that exoplanet is. And then the frequency of the dimming tells you what the period of the orbit of the exoplanet is. So lots of good information that you can get there just by looking at the dimming of that star. And there are many telescopes like Kepler, which is now retired, and the TESS mission, the TESS satellite, which are able to do this for hundreds of thousands of stars at a time. And we recently, now almost a year ago in March, we crossed the threshold of 5,000 exoplanets that we know of. But we think there are likely hundreds of billions of exoplanets in our galaxy alone. So lots and lots of exoplanets to explore. So we've already started looking at these exoplanets using the JWST. And one of these exoplanets had a really, really good, good detailed study on it. It's called WST 39b. So located 700 light years away. And this type of exoplanet is what we call hot Jupiter. So it's big and puffy like Jupiter, but it's very close to its star. So we know on Earth, it takes us a year to go around the sun. The closest planet to the sun is Mercury. It takes it 88 days to go around it. It takes WST 39b about 4 days to go around its star. Very, very fast. And the surface, the atmosphere of this planet is about 900 degrees Celsius. So this is why we call it a hot Jupiter, essentially. So many people looked at this planet with one of the first programs that used data from the JWST. And many of those people were my collaborators, my colleagues at the University of Montreal. So we have Bjorn Beneke, who's a professor, and many of his graduate students and postdocs that you can see here. I'm just going to move this one so you can see my face. Okay, that seems fair. So yeah, fantastic. And they basically worked lightning fast to try to analyze this data that basically only came in August. And they already have really fantastic results. But the results that they have are a little bit trickier to explain than just showing you a beautiful image. So we'll walk through this a little bit more carefully. So this is what we call a transit light curve. So you remember I was saying the transit method is one of the ways we can find exoplanets. It's when the exoplanet passes in front of the star and some of that starlight is blocked out. So this is the signal that we get. So here you can see when nothing is in front of the star, starlight is at 100%. But when the planet passes in front, it'll dip here. And in this case, about 2.5% of the light is lost when WST 39b passes in front. And let me tell you, this is beautiful data. Usually the transit light curve that we see from telescopes that are smaller than Webb are really, really noisy. You don't get something so clear as a signal. So this is really fantastic data. Now, this tells us the exoplanet is there, it exists, but we use the magic of spectroscopy to get even more information. And this is where instruments like the Canadian instrument within the spectrograph comes in. So what is spectroscopy? So this is essentially a technique we use when we take a kind of light and we break it apart into its constituent colors. Now, the most sort of easy way to think about this is if you're thinking about visible light. So you take white light or sunlight, you put it in a prism, you put this on a Pink Floyd album, and then you diffract the light and you make a rainbow. But you can do this with any kind of light. It's just a little bit more abstract. You can take infrared light, you put it in a spectrograph, you break it apart into its infrared colors. It's just that everything is sort of invisible to us. And something really magical happens when you're using spectroscopy around stars and around exoplanets. So here you have a beautiful rainbow, which is a spectrum of the sun, but you see it's not a perfectly clear, clean rainbow. You see all these little black marks all around. So the black marks are actually like a barcode that's telling you the elements that are inside the atmosphere of the sun. Something similar can happen when an exoplanet passes in front of a star. So what happens is the starlight will stream through the atmosphere of the exoplanet, and some of that color will actually be sucked out and leave these little black marks, and that will be the barcode of the molecule that exists in the exoplanet's atmosphere. So this is the signal that we read. It's called a spectrum, and all these little bumps and wiggles are signatures of specific molecules that we can find in the atmosphere of these exoplanets. So this is the spectrum from the Canadian instrument nearest there. This is one coming from NIRCam, the American instrument, and these two from NIRSpec, which is European instrument. Again, very complementary between all of them. And between all of these different instruments, we were able to basically do the most detailed study of any exoplanet atmosphere ever to date. We were able to find potassium in the atmosphere, the same thing we have in our bananas, water vapor, carbon monoxide, carbon dioxide as well, and sulfur dioxide. And sulfur dioxide here we think was actually created through something we call photochemistry. So the star's light interacts with the molecules in the exoplanet atmosphere and causes the creation of the sulfur dioxide. And on Earth, the ozone layer is created in a similar fashion. So we've never been able to look at an exoplanet in so much detail. So it's really, really exciting times. But you might say, okay, this is cool, but I want aliens. Show me the aliens. And Lost 39b is not a really good candidate for that because, again, it's very close to its star. It's a gas giant. It's 900 degrees. This is a really good test bed for the Webb telescope, but we have lots and lots of more Earth-like targets that we have already observed. We're analyzing the data and we will be observing. You might have heard of the TRAPPIST-1 system, which has 7 Earth-like planets. 3 or 4 of them are in a zone we call the habitable zone, where the temperatures are more Earth-like or water could be in liquid form. And we already observed those planets and we're analyzing the data right now. So we are able to do this with all different kinds of planets. Now, I said that the best way to study and find exoplanets is these indirect methods, like the transit method. But every once in a while, you get lucky and you can actually take a direct image of an exoplanet. And we have a great history of that here in Montreal, in Quebec, and in Canada. The first ever direct image of an exoplanet system of 4 different exoplanets was taken by a Canadian team that includes 2 of the members that we currently have at the Trotsky Institute for Research on Exoplanets. So they were able in 2008 to take a real image of these exoplanets. Really, really fantastic. And that is one of the reasons why we have an Exoplanet Institute at the University of Montreal. So there are specific conditions we need to be able to do this. And essentially you need a big planet that shines some of its own light or reflects a lot of light from its star. So when I say big, I'm talking about 10 times more massive than Jupiter often. So even bigger than Jupiter. And they need to be quite far from their star. Otherwise they get lost in the glare of their star. So very big, quite bright. It helps that they're young because when they're younger, they shine more brightly as well and far from their star. And you need to often use what we call a coronagraph, which is a mask that hides the very glary sunlight of the star at the center. So this was the first exoplanet image by the JWST. It's called HIP 65426b. And this is still a very large planet, larger than Jupiter. But because Webb is so large, it has such a big mirror, we think we will be able to directly image planets that are on the size of Saturn, maybe even Uranus and Neptune with the Webb telescope. That's very, very exciting. Now, of course, the image is just, you know, it's a dot. You don't see like all the detail and like little creatures walking around on the surface, of course, but you still get lots of valuable information when you're looking at the direct light of the star. Now, moving now to the life cycle of stars, this is sort of like a fan favorite, a crowd favorite when the images were first released on July 12th this summer. This is called the Carina Nebula, or we nicknamed it the Cosmic Eclipse. It is what we call a star-forming region, so a big cloud of gas and dust, or stars are being formed in here. And this is really fantastic to look at in the infrared. Now, the visible light tends to be blocked out by all this dust, whereas the dust is sort of a little transparent for the infrared. So because we're looking at the infrared here, we can actually peek into these little caverns right there. And that golden light that you see is the very early lights of newborn stars, a few million years old, that are amassing lots of dust and heating that up and being born and igniting their own hearts. So you can see that only because of the infrared. And you can see sort of this landscape. All of this is due to all of the stellar radiation of stars at different life cycles, different stages of their evolution that are sort of eroding away at this material, pushing down. So this whole landscape is basically carved out by these different stars at different stages of their early evolution. So this is a comparison of what you can see using the Hubble telescope in the visible and the Webb telescope in the infrared. So you see a lot more information, not only because Webb is a larger mirror, but because you're looking at infrared light. So it's truly important to use infrared light to lift that cosmic dust veil on these types of nebulae. Now, going from the birth of stars, we can now go to the death of stars. This is what we call a planetary nebula. It's called the Southern Ring. And the planetary nebula is what happens when a fairly average star, like the sun, ends up dying. So what happens is it sort of puffs up into what we call a red giant. Eventually it runs out of fuel, runs out of gas, and it expels its outer layers of gas. And these are what you see here, all of these subsequent layers of these shells that are sort of bringing out. That is the star as it's dying that is blowing out these layers of gas and dust. And what you're left with at the center is what we call a stellar remnant, which is a white dwarf in this case. For more massive stars, you can end up getting a neutron star or a black hole at the center. Now, one might say, okay, I'm expecting shells of gas and dust and a white dwarf at the center, right? I see the shells of gas and dust, and I see this, that must be the white dwarf, right? Actually, it's not the white dwarf. For you to see the white dwarf, you actually need to look not only at the near infrared with the NIRCam instrument, but at the mid infrared, slightly longer wavelengths with the NIRI instruments. So here, you can actually see two stars at the center of the planetary nebula, and that's because there's a binary system at the center. So two stars that are locked in orbit together, that are co-orbiting, and the one that is very bright and blue is actually still alive. The one that recently died and exploded is this one here. And even though it's called a white dwarf, it appears more red because it's still enshrouded in layers of dust. And it's heating up that dust, and that dust appears red. So you need to look in the mid-infrared to look here. So really fantastic showing of you need to look at all different kinds of light to be able to get the full picture. And even though a planetary nebula is like the main focus of this image, one feature that I love in all of the images from the JWST is how much you can't get away from all these background galaxies all around. And this one here, this is a perfectly edge-on spiral galaxy. So it looks like a light ray, but this is actually a whole galaxy that you can see embedded right there. Speaking of galaxies, we can look at these 5 galaxies, which is called 7 quintets. They are a group of 4 interacting galaxies and one that sort of looks like it's part of the group, but only because of it's in the field of view. And you can actually see these 2 galaxies right here, which are in mid-collision. Their cores are very close to each other, and they're interacting with this one right up here. What you see in the orange is a gas shock wave. As the galaxies smash together, that gas is compressed and actually leads to a bunch of star formation happening. So even though it's sort of a destructive event, you have creation coming out of it through this gas colliding and creating those new stars. But if you look again now in the mid-infrared instead, typically stars don't shine very brightly in the mid-infrared. The gas and the dust in galaxies is really what shines in the mid-infrared. So you're left with what I like to call gas skeletons here. So you're sort of getting X-ray visions here just by looking at the mid-infrared instead of near infrared. You have all of these sort of little spiral arms embedded in the galaxy, which will eventually turn into stars as well. And you might notice that this galaxy up here, the center suddenly looks much brighter in the mid-infrared, and that's because there is a really big black hole, not the technical term, a supermassive black hole, at the center right here, which is actively feeding on dust. And that dust is again being heated up as it's falling into the black hole, causing this to be very, very bright. And we've been able to take spectra from that region there and tell what kind of elements, silicates essentially, that are falling into the black hole, how fast the material is moving around the black hole, all kinds of really interesting information. Now, if you want galaxies, this is really the picture for you. There's about 7,000 galaxies in this image alone. This is what we call the Webb deep field of galaxies. And this image, you might think, is a huge part of the sky, but it's actually only the equivalent of a single grain of sand on the tip of your finger, held up at arm's length. So in that tiny part of the sky, there are these 7,000 galaxies. And you can see many different galaxies, all different kinds, shapes, colors. This number here is for a galaxy cluster, which is in the foreground, only about 4 billion light years away. These very large white galaxies are there. Everything sort of in the background, smaller, redder. Those are very, very distant background galaxies. And one of the reasons why we built Webb to be an infrared telescope is because we knew those galaxies were going to be very red and actually infrared. So if you're looking at the same part of the sky with the Hubble telescope, you can tell that there are many, many less galaxies in the background because you're looking at visible light. So because of a phenomenon called redshift, caused by the expansion of the universe, as galaxies are pulled away from us by the expanding universe, their sort of bluish, ultraviolet visible light is stretched out and turned into red or infrared light. And this is even more of an effect the farther out you go. The farther the galaxy, the more that redshift is important. So in order to look at the very first galaxy ever created after the Big Bang, you absolutely need to look at the infrared. So that is one of the reasons why we built the Webb telescope, to look at the infrared. If you look closely, you might see some more interesting stuff going on. Here you have these sort of weird warped little lines there. Those are actually those distant galaxies that have been deformed because of a phenomenon called gravitational lensing. So you can see some close-ups of them here. So essentially what's happened here is you have that foreground cluster that I mentioned, that 4 billion light years away, which is so heavy that it's deforming the very fabric of the universe. It's deforming space-time, and it's deforming and warping that light from distant galaxies. So the background galaxy here, the light will go around it and look really weird. And sometimes you get really perfect alignments and you get what we call an Einstein ring, which is seen here. So you might think, oh, that's not good. Like you're deforming the galaxy. I can't even tell it's a galaxy anymore. But often what happens here is the light from the distant galaxy is magnified, sometimes 3, 4, 5 times. So you're actually able to see things that would otherwise be too faint for you to see. And sometimes that image of the galaxy is actually doubled up. So you end up seeing 2 images of the same galaxy. But how can you tell it's the same galaxy? By comparing the spectrum. So it's sort of, again, this idea of these spectrums being fingerprints. So using here, the nearest Canadian instrument, we took a spectrum of this galaxy here, we took a spectrum of that galaxy, we compared them, they looked identical, so we knew that it was a double image caused by that effect of gravitational lensing. Now, I've been focusing a lot on things outside the solar system, but of course, as I mentioned, Webb can look at things inside of our solar system. This is a beautiful image that was taken of Jupiter with auroras visible on both the northern and southern pole. You can see the big red dot that looks very white here. It's a big storm. We see also the rings of Jupiter here and some of its moons. It's a beautiful picture, of course. But one thing I really love about this picture, it was not actually created by anyone that is part of the JWST team. It was actually created by a citizen scientist, Judy Schmidt, who is a student in California, not in astronomy, and she took publicly available data from the Webb telescope and processed the image herself. So that means that if you are patient and you're willing to learn, you too can make beautiful images from the Webb telescope. So she had she taught herself how to do this for 10 years with the Hubble telescope. She's been doing this for a little while, but most of the data from the telescope is publicly available online. So anyone can essentially use that. Now, looking at stars again, when you think of a star, you probably think of either the sun or like a little dot in the sky, but there are particular stars that are very active called Wolf-Rayet stars. They're at the very, very end of their lives and they're blowing up lots and lots of material from their star, their bodies. This is what a Wolf-Rayet star looks like. And recently, we looked at a particular Wolf-Rayet star, which is in a binary system. And so it is a Wolf-Rayet star. It's co-orbiting a normal star. But something weird happens. Every time they have a close pass, it activates the Wolf-Rayet star. And so on this about 10-year-long orbit, you will have these flares of lots of material that's pushed out of the star. And what does that look like? In the visible, it doesn't look very interesting, but in the infrared, the mid-infrared, this is what you see. You actually see this really interesting sort of tree ring pattern where every time you see a shell or a ring, you know that about 10 years have passed. And this is only visible because it's in the mid-infrared where the dust itself is shining. And a lot of that material will end up being blown out of the system and go on to forming other stars. So you are sort of like in a big recycling factory, and all this material blown out from a dying star will lead to other stars later on. Now, this is my favorite picture from the Webb telescope. We're coming to the end with some of the last few images in the last few weeks. The Pillars of Creation I mentioned was a very iconic image taken by the Hubble telescope. You can see it here. But now, using the Webb telescope in the infrared, you can see from a brand new perspective. So again, this is a star-forming region where lots of stars are being born in the Eagle Nebula. And you see lots of interesting things in the visible, but a lot of it is sort of hidden or shrouded in the dust. When you're looking instead of the infrared, suddenly you gain access through the dust at all these stars that are being born. And I especially love these sort of lava crevices that are glowing, these crimson glowing crevices in the fingertips right there and in some other regions. It's sort of like those golden caves that we saw in the cosmic cliffs of the Carina Nebula. So very, very young protostars are being born inside there. And you have that gas that's shocking with the energy of the star and causing this sort of interesting glow. So you can gain a lot more access and information when you're looking at the infrared. And if you look at the mid-infrared instead, I'm having to like play around with the zoom thing all the time. If you're looking at the mid-infrared, again, we're taking away almost all the light from the stars, and you're left with this ghostly hand of only the dust. So we put this out for Halloween. It looks quite creepy. And to look at a little bit closer at some of those protostars, very, very early stars that are being born, this is one of those stars right there from a close-up. So we can see more detail, not just inside of a nebula. And at the very center here, you have basically a baby star that's barely a star yet, that is blowing out lots of gas and dust and interacting with its environment and causing this sort of like hourglass pattern in what we call the dark cloud, L1527. And this is a picture that was just released today, so I'm going to end with this. This is two galaxies that are merging together. It was taken by the Hubble Space Telescope as well earlier, but here in the infrared, you can see a lot of the new stars that are being formed in those shockwave patterns that I mentioned before. All these really glowing bits, that star formation that's being created by all of the gas being pushed together as the galaxies are colliding. So all in all, really beautiful pictures, but I remind you, we've only been taking data for about 6 months. This telescope will be operational, we hope, for another 20 or so years. So this is the tip of the iceberg. I'm very fortunate I'll be going to Baltimore at the Space Telescope Science Institute in a few weeks to meet with my colleagues and hear all the fantastic scientific results that they're working on. But there's so much left to look forward to. And in Canada, we have lots of exciting results as well. So I hope you stay tuned for that. Thank you. Do you want to moderate or do I moderate myself?
I guess we could do a little bit of both. I can check if there are any questions on.
I managed to ignore myself for like 50.
Yeah, that is. So let's see. Are there any questions? So there are no questions online yet. So if you want to take questions.
Sure. Are there any questions in the room? Yes.
So I was wondering about the color mapping, the font color. So like the different instruments have different spectral windows. Do you have like a standard within your optic infrared astronomy community of like trying to map certain colors to certain windows, or is it completely like artistic liberty with the color mapping like outside of citizen science, like within the teams? Have you guys all agreed upon something there, or is it going to be this like violet to red, 1.3 to 1 micron or 3 micron, or violet to red when it's 2 to 5?
So the question is there a standard for how we map invisible infrared light to make these colored images? And there is a standard in the sense that we usually take a full visible spectrum that we can see and we map it onto whatever the wavelengths of the image is, where whatever shortest infrared wavelength will track to violet, and then whatever longest wavelength in the infrared will track to red. So for the most part, this is what we use. Basically, we just take longest to shortest wavelength and we map it the longest to shortest on the visible spectrum. That being said, there is a little bit of artistic license for scientific reasons, not to be fake images or anything like that. Sometimes if you want to highlight, for example, hydrogen features, you want it to be a certain color. And there's actually a lot of really interesting work being done on understanding human eye anatomy and psychology, so they were actually conveying the correct thing. So certain images, certain colors convey a direction. So a certain color can look more on the foreground or the background. And so if we know that that part of the image is moving forward or backwards, we want to make sure that the color we choose conveys that movement, knowing what we know about the human brain's interpretation of those colors. So there is like a simple mapping, short to long wavelengths to visible, but we play around with it a little bit because in the end, we're all doing it in the hope that we convey the scientific information as effectively as possible. Yes?
I'd like to know, how is the research managed on the telescope? I guess you're not moving it all the time towards another object, so you have to reboot research, I suppose, looking far, looking close. How is this done on a day-to-day basis?
Yeah, absolutely. So the question is, how do we sort of schedule out how we point the telescope, what we're looking at any given time? And so this is the case for most professional telescopes. These schedules are settled many, many months in advance. So every year we have what we call a cycle. And before that, the year before, different astronomers have to submit proposals for scientific programs that they're interested in. And then there's a competitive process where their proposal is graded. And for the last cycle, only 1 out of 4 proposals was retained. And sometimes it can be as low as 10% of proposals, and it's very competitive. Now, once all of the interesting programs are selected, you then have to try and use your telescope time as efficiently as possible. So there are certain constraints. For example, we know that we can't point the telescope towards the sun, which means that not the entire sky is accessible to the telescope at all times. So we need to take that into consideration. If like the sun is here, the telescope is here, and I want to point over there, well, I'm going to have to wait a little bit until that's accessible.
There are certain events also that you need to time. For example, if you want to look at an exoplanet transit, that doesn't happen all the time. You need to know ideally when that will happen, and that is considered in terms of when that program will be put into the schedule. So there's a lot of work that's done, some automation, but a lot of human oversight as well. But it's done very effectively. And the telescope for Webb, about 60 to 70% of the time is used where it's really taking scientific data. To compare Hubble, it's only about 20% of the time. So we've really been able to make the use of this telescope as efficient as possible and make the $11 billion really worth it. Yeah. Very good question. So the question is, what would happen if one of the mirrors on the telescope would break? And this is something that we know can happen, for example, from a micrometeorite hit that I mentioned. So this is where the different segments being independently movable helps a lot. One example I can give is last May, at the end of May, there was one micrometeorite hit that was larger than we expected. We didn't think that this was going to happen so early on in the mission. We knew that they were going to happen, but it was a bit of a surprise. And there was sort of like a blemish left on that segment. But the other segments were adjusted, aligned in such a way that we're reforming the mirror so that that blemish almost sort of disappears. And if one whole segment were to be completely blown out, you have a lesser telescope that's still functional because you can still move the other segments around. But I can tell you with a micrometeorite hit, we expect about one per month. We have sort of like in our idea, okay, it's sort of like real meteorites or real asteroid hits here, like something that's going to like make everything extinct will happen like once every 100 million years. Well, if you happen to be really unlucky and you're born the day before that hit happens, you can't say like, oh, well, it happened, you know, within me, like 1 year of me being born, it happens every year. You just got really unlucky. And we think that's what happened. The bigger hit happened early on in the mission, but we're continuing to sort of study that. That's one thing that we want to do. We want to sort of quantify how many micrometeorites exist in that part of space too, so that future missions can use that knowledge. Yes. Oui, c'est bon. Le carburant, hein. Donc, la question, c'est quoi les autres facteurs qui déterminent la durée de vie pour la mission? Donc, c'est vraiment le carburant qui est le facteur le plus déterminant parce que le télescope, lui, orbite autour d'un point qu'on appelle quasi stable. Donc, il n'y a pas besoin de beaucoup de mouvements ou d'ajustements pour rester en orbite, mais il y a besoin d'un micro-ajustement toutes les 3 semaines environ. Et si on n'est plus capable de faire cet ajustement, là, on n'est plus capable de bien pointer le télescope. On perd un peu de contrôle, éventuellement, le vent solaire pousse sur la voile solaire et ça fait que le télescope, genre, il perd un peu son orbite. Ça, c'est vraiment le facteur limitant. C'est là où on a vraiment sauvé le carburant et ça a prolongé la durée de la mission de 10 à 20 ans. Un autre facteur, par contre, c'est les instruments eux-mêmes peuvent avoir des défaillances avec le temps. On espère qu'ils vont continuer à fonctionner correctement, mais on sait que ce n'est pas toujours le cas. Et je dirais que l'instrument qui est le plus fragile, le plus susceptible à arrêter de fonctionner avant la fin de la durée du carburant, c'est l'instrument MIRI, qui est dans le moyen infrarouge, le Mid-Infrared Instrument, parce que c'est lui qui a le réfrigérateur supplémentaire pour le refroidir à 7 degrés Kelvin. Et ça, c'est un équipement supplémentaire qui pourrait arrêter de fonctionner, ce qui voudrait dire que cet instrument ne fonctionnerait plus. Donc, tous les instruments pourraient arrêter de fonctionner. C'est sûr que si un astéroïde gigantesque rentrait dans le miroir, ça serait un problème. Mais en général, c'est vraiment le carburant, le réfrigérateur de MIRI et si d'autres composants électroniques dans les instruments fonctionnent plus. Other questions? I'm happy to go back to English or French. Oui.
What was the planning of the mission on the cost of like originally was 10 years, but instead of 20, and it wasn't after putting the whole maybe we'll 10, 20 years without the year, but we would think that in 20 years perhaps we'll be able to service it so we can claim more
So the question is there any potential for extending the mission even beyond 20 years so that it can be serviceable? So it wasn't designed to do that. We would need to find a way to do that with the items that we put on the telescope now. There are some very optimistic people who say, yes, we can do it. Human innovation is the greatest thing ever, and perhaps. But maybe at that point, we will have found other technologies for spectrograph detectors, and we will want to put that on another telescope. We're already currently, we haven't started building it or anything, but we're envisioning the successor to the JWST, which is a sort of similar looking telescope, but then would simultaneously look in the ultraviolet, the visible, and the infrared, with a mirror that's, I'm hoping 12 to 15 meters wide, but that's very optimistic. Maybe like 6 to 9 meters wide, but very, very similar in look. So it's true, human innovation is very surprising. Maybe we'll find a way to service it and put some gas in it and make it continue working. But certainly there are other missions that we're planning on already that would be complementary or would be a great follow-up on the JWST. Yes. Yeah, so we've gotten really good at talking to things that we sent quite far away using a specific set of telescopes called the NASA Deep Space Network. And this is 3 radio telescope or radio dishes that are on the Earth, and they're scattered a little bit all over. There's one in Australia, one in Spain, one in the US, which means that there's always one of them that's pointing at deep space, which is really handy. So they are really overloaded in terms of work. They talk to everything that's in deep space, the Voyager probes, when with working Cassini, Juno, everything that's like really, really far out that's talking to them. So what happens is there's a radio dish under the sun shield. Well, not a radio dish, but there's an antenna essentially on the JWST under the sun shield that's pointing back to Earth. And it is sending data. While we were doing the commissioning, we sort of had priority because we didn't want anything to go wrong. So we were sort of in constant contact with the telescope, making sure everything was okay. Now, about every 6 to 12 hours, we get like a huge download of data of all the backlog of data that the telescope collected that day. And that is then streamed immediately to the Space Telescope Science Institute, where we process that data and deliver it to the public and to the astronomers who ordered the data in the proposals. Yes. So the question is, are there any specific programs that the Université Montréal is working on with JWST data? And so WASP 39B is one of those, and we just released those first results a few weeks ago. That was very, very exciting. TRAPPIST-1, we have some first results that we can't talk about too much, but in the new year, we'll be able to do some press releases around that. That's super exciting. There are others that are LADO worlds. So these are rocky planets that are very close to their star, and their surface is basically an ocean of magma, and their atmosphere is vaporized rock. So very extreme world. Not good for alien life, we think, but still very interesting in general. We also have some people that are looking at what we call brown dwarfs. Brown dwarfs being sort of like this weird object that's like, some people call it a failed star, or some people call it like a super planet. That's like really quite a bit bigger than Jupiter, but doesn't have the nuclear fusion in its heart that qualifies it as a star. So mostly it's things related to exoplanets and brown dwarfs and protoplanetary disks where stars and planets are being formed. Yeah, maybe at some point I'll find time to ask for some data for galaxies. I haven't decided yet. I tend to work more with the ground-based telescope data. Yes.
Let's look at this data about the new exoplanet or galaxies or stars. How does the based on data then you estimate the distance, and what accuracy, after the accuracy can you estimate the distance?
Yeah, so the question is, how do we know how far away these exoplanets are? And we do that by knowing how far away the star is. So with the stars, we have what we call standard candles or a cosmic distance ladder. So there are different things that you can do for different types of stars. Some of the closest stars, we use what we call the parallax effect. So it's quite simple. You can do it yourself, not with a star, but like with your finger. If you pretend that the Earth is orbiting around the sun, and when it's in one location, that's the equivalent of one of your eyes, and then on the other side, it's your other eye. If you're looking at a very distant star, because of that slight difference in your location, your point of view, that star will look at a little bit in a different point of the sky. So you can actually do that with your finger and your eye. I look really weird right now. You should all be doing it right now. You're like me. So if you put your finger out there and you open only one eye and you switch eyes, you'll see your finger kind of jumps a little bit. So the same thing happens. And the closer your finger is, the bigger that jump. So you can measure that jump and you can actually tell, okay, that's how far. It's just simple trigonometry. You can tell how far that star needs to be for that jump to happen based on like the different location of the Earth. There are other things too. Certain types of stars are called Cepheid variables, and they change their brightness. And the change in their brightness is directly correlated to how bright they are absolutely. So if you can see, it's what we call its apparent magnitude, how bright it appears. And because of the period of its variability, you can tell how bright it's supposed to be. You can tell again how far away it is. So we have all these little tricks to know how distant these stars are. And then we assume the planet is like basically at the same distance.
So there's a question online. How is there so much dust or gas in the pillars of creation that it can create so many stars so far apart? Where does it come from and accumulate? And I guess I'll add, like, what is it?
What is the gas and dust? Yeah. So it's sort of like this concept of the cosmic recycling factory that I mentioned. So a lot of that gas and dust is from previous generations of stars that when they died out, they exploded into a supernova, into a planetary nebula. All of that gas and dust was pushed out into the rest of the galaxy, into interstellar space, essentially. And eventually, all of that gas and dust will meet up with other pieces of gas and dust, and through the force of gravity, it will sort of like start collecting together like dust bunnies, essentially. And you can end up getting condensation of these different areas in the gas and dust, these pockets, where you will have small areas that will collapse in on themselves in what we call giant molecular clouds and turn into new stars and solar systems. They will live their life, they will die, they will blow out all of that material, and the whole cycle continues again. So this is how all of this gas and dust exists around. What were the first stars created from? So this is what we call population 3 stars. Why is the population 1 star? That's a good idea. Astronomers did a bad job naming these stars. So we think these were like the very first stars created right after the Big Bang. Super, super massive. Probably didn't last very long. And they created sort of like that first gas and dust. How are they created? That's sort of a mystery that we're trying to solve with some of these really large telescopes that can look very, very far back. Now, what is the actual gas and dust? It's kind of similar to what you have left over after you light a fire in your fireplace or you do a barbecue, that sort of soot and ash. And apparently, we can sort of look at the molecular composition. It smells like a barbecue out there. It smells like a sort of ashy, sooty barbecue. Yes. Yeah, so the question is space garbage or junk or debris or whatever you want to call it a danger to us? So this is all of the satellites and the debris that are in orbit around the Earth. Because we launched it there, satellites that no longer function, or maybe pieces that have like sort of collided together and created these clouds of debris. Certainly, the more there is up there, the bigger of a problem it is. We're not at the point where we have to fear for our lives that like a piece of space junk is going to fall on our heads. But we may eventually get to a point where the chance of some of these different pieces, some of them with people on it, like the International Space Station, might be at risk of colliding with something else. And that would be a problem, especially if you think of the possible domino effect that would happen. You have 2 pieces colliding, you make this like huge cloud of shrapnel that is now orbiting around the Earth and colliding with other pieces. Everything can end up breaking apart. So I think it's very important that we regulate what we put up there and that we have a plan for when a satellite stops working, how do we decommission it? And usually what happens is we try to deorbit it gently so that it falls back through the atmosphere of the Earth where it burns up. But not all nations are on board with this. So space policy is a very active field currently that needs much more legislation, I believe. And I think McGill actually has a very active space policy and space law program. Do I still have time for questions?
We have time for one or two more.
Okay, all right. Yeah.
I really wouldn't be working on this if we don't know what's successor, but what are other projects that complementary as well?
So the question is, what are some of the other projects that are complementary to the JWST? That's a great question. And actually, we're working on some really fantastic ground-based telescopes that will be complementary. So the next generation of these telescopes that we call giant telescopes will have mirrors that are 3 to 4 times larger than the currently largest ones. So currently the largest visible light telescopes are about 10 meters wide. And they're very, very large. And typically we need to start thinking about making them in segments as well, because they are crushed under their own gravity. You can't move them around properly. The next generation will have mirrors 30 to 40 meters wide. And so one is currently under construction in Chile by the European Southern Observatory. And we're trying really hard, a bunch of astronomers in Canada, all over the place. I know there's people in McGill, University of Montreal. We're trying to contribute to an instrument that will be on that telescope so we can have access to that telescope. So that will be 39 meters wide. It will be the largest telescope ever when it sees its first light in the end of the decade, like at the end of the 2020s, essentially. And we have a few other giant telescopes in the works. So they will be able to do fantastic things because their mirrors or light buckets are so big. So they will be crucial in finding or maybe confirming biosignatures, signs that there's a biological life on these exoplanets using their really, really strong mirrors who can pick up very weak signals. It'll also be really, really great to take real direct images of exoplanets, for example. And I am really looking forward for those telescopes because I study a lot of dwarf galaxies, which are very faint. Currently, on the largest telescope, I need to stare at my dwarf galaxy for 5 hours for a single galaxy. And I work in the Virgo cluster that has over 4,000 members. And people don't like me enough to give me all their telescope time. So having a really big mirror is going to reduce my observing time per galaxy greatly. So those are really exciting complementary missions that we're working on. Yes.
What's the best resource or resources for interested non-scientists to continue to track interesting output and the interesting research?
Yeah, absolutely. So for our institute, we just launched a brand new website last week. I'm super proud of it, a really great resource. We put out all of our press releases there, but also really good if you want to just have a basic knowledge of what's an exoplanet, what are some of the big discoveries. We wanted it to be a good resource for children and students as well. So it's exoplanets.ca. For the Webb Telescope, webtelescope.org is the main source where all of the first images and lots of complementary information and infographics related to the first images is located. You can also go on the Canadian Space Agency website where we talk about our contribution, and there are a lot of resources for educational programs as well. That's a perfect final question. Thank you.
Perfect. So let's thank Natalie one more time. So before you all go, oh wow, that really is.
I know, right?
So
Isn't it so
annoying. Well, we will pause the live stream now, because now we have our raffle and we have 2 winners. The winners are Charles and Laurent. So you can find me after and get your very Now vintage collectible McGill Space Institute mug and hat. Last but not least, I just want to thank everyone for coming. I see a lot of familiar faces who have been attending the 4 public lectures that we put on this fall. So hopefully we'll see you again next term. We host public lectures on the last Wednesday of every single month. So follow us on Facebook, Instagram at TSI McGill, and have a wonderful night.
That's never happened.